We begin, just another reminder, please check your phones, laptops, anything that makes annoying noises during talks. Make sure they won't make annoying noises during talks. And actually look at your phones, take them out of your pocket. Make sure they're quiet. That'd be really useful, thank you. We'll just wait for these last few people to come in and then I suspect the doors will close. So welcome to the first of these stream sessions at PyCon 2017. Our first presenter today is Victor Stinner, who is going to be telling us about optimizations which made Python 3.6 faster than Python 3.5. Please make Victor welcome.
So hi everybody, I'm here to tell you which optimization made Python 3.6 faster than Python 3.5. I'm Victor Stinner. I'm working for Red Hat on OpenStack. One of my job is to port OpenStack to Python 3. And the good news is that most unit tests pass already on Python 3. So we have close to port this giant project, which is something like 3 million lines of Python code ported to Python 3. And sometimes I'm also working on Python. So we will first start to discuss how to get stable benchmark. We'll receive the results of the different Python version to finish with the optimization of the different version of Python. So benchmarks. 1 year ago, in March 2016, in fact, almost no one trusted the benchmark of Python because if you run the same benchmark twice, once it will take that the benchmark makes Python faster, and the second time it will say that the benchmark makes Python slower. So we didn't know if we should trust them, and some people just decided to only focus on micro benchmark or just hope that maybe it will make Python faster. So to fix this issue, I started to write a new module called perf. The perf does different things. First is calibrate the number of loops to run the benchmark long enough. It spawns multiple processes in sequence. It computes 3 values per process, so to get a total of 60 values. It's important to spawn multiple processes because, in my experience, each process will get different performance, and it's nice to have all kinds of values to be able to get more stable results, which means more reproducible results. What you can do with all these values, in the old version of the benchmark suite, we use the minimum. But if you use the minimum, there is a known issue called the local minimum, which is that if you run the benchmark once on the benchmark a new time, you don't get the same value because you need a very long list of values to really find the minimum of your computer. And if you use the average, it's much more reliable because you smooth the values between the maximum and the minimum. And another important tool coming from statistics is the standard deviation. It gives you an idea of the range of where most of your values are. And it also gives you an idea of the stability of your benchmark. Because if the range is too big, it probably means that you have an issue on your benchmark, or maybe that you have an issue on your system. The performance project is a new project hosted on GitHub. It's a new version of the benchmark suite, now using perf. And the good news is that the speed.python.org is already running performance. So to get stable results, my first issue was the code locality. It's something related to very low-level stuff of the CPU, because depending on the exact layout of the code in memory, you don't get exactly the same speed. And to get stable results, you can use LTO, which is a link time optimization, but also the PGO, profile guided optimization. And the other kind of issues is the system itself and the hardware. It's not easy to explain everything in a few minutes, but in short, just use my command perf system tune. It will tune your system to run benchmark. So, for example, it will use the fixed CPU frequency, because you have to know that nowadays CPUs are not running at the same speed every time, all the time. In fact, the frequency is changing like all the time in each core of your CPU. And depending on the workload of the other CPU, depending on the temperature, depending on a lot of stuff, you don't get the same speed. So that's really, an important issue. And the workaround is to use the fixed frequency. But also, you have to disable the Intel Turbo Boost. It's a feature of Intel CPU. The idea is that if you only have one core active, it means that the CPU can run, for example, 20% faster, because the CPU tries to limit the power consumption, but if there is only one CPU active, it is able to use more current for a single CPU. So we don't just want to disable this feature, so we don't depend on the workload of the other CPUs. And Linux has a super cool feature called CPU isolation. In short, the idea is that you tell the scheduler to never schedule any kind of task on one specific CPU or a CPU set. And later, you will pin your process on this specific CPU, so you will be like alone on the CPU. You will not get any kind of interruption, and it makes the benchmark much more stable. So now we have super stable performance. What super stable benchmark results? What can you do with that? The very cool thing is that you can very easily spot a performance regression, because it becomes now obvious. For example, this one is a real example on Python 3.6 during the development cycle. The Python startup is a time to start Python before starting to execute in your own code. And the old performance was 20 milliseconds, and suddenly it becomes 27. In fact, it was something related to a new import somewhere in the code. The good thing is that we spotted the issue, but also that we were able to make Python even faster after the fix. Another important thing, in my opinion, is the timeline. Today we have results over 3 years. And it's important to see the whole timeline, because sometimes we tend to focus on very tiny things, on micro benchmark, or on very small issues. But it's good to have the overall pictures of your whole application, to have an idea of the performance and the trend also. For your information, this one is a telco benchmark. And the good thing is that we are getting faster and faster. Okay, now the results. As announced in the title, Python 3.6 is faster than Python 2.5. These results are normalized to Python 3.5, which means that lower means faster. I wasn't able to display all results because there are something like 60 benchmarks. So I only picked the one which are the most significant. And if you still have to be convinced, Python 3 is faster than Python 2. And I think that today it's even more right than it was a few years ago, because you can now see that the difference is quite significant on this benchmark. If you are using SymPy, the good news is that it became between 22 and 42% faster, which is quite good. It means that only by changing the version of Python, it becomes much faster. And just for the fun, there is an interesting benchmark, which is a telco. Basically, it's a benchmark on the decimal module. The decimal module computes a number using the decimal base and not the binary base. And Stefan Kra rewrote the module in the C language in Python 3.3. And today we are simply 40 times faster in Python 3. Another very good news is that even if Python 3.6 was released only a few months ago in December, we are already faster than Python 2.6. The thing is that we had some optimization prepared, but we decided to not merge them just before the release, to not take a risk of introducing regression. So we pushed them just after the release. And it's already quite faster. Okay, I would like to focus on some optimization made in Python 3.5. What I did is to analyze the results on the timeline and try to spot which optimization were the most significant on the timeline. So in Python 3.5, the Matt Joyner, Alexei Kashayev, and Sergei Storchaka re-implemented the functools.lru cache in the C language. It made the SymPy 20% faster and SciMark LU 5% faster. But it was quite difficult to implement this optimization because a cache is something quite complex. There are many corner cases, and if you convert your code to the C language, you have even more tricky issues. So it took something like 3.5 years to close the issue, to implement the optimization. In Python 3.5, Eric's now re-implemented the collection.orderedict in the C language. It made HTML5 lib 20% faster. And the implementation is based on the implementation of the Python dict type. And again, it was very tricky because even if the API seems simple, there are many corner cases, and it took a lot of time to design new tests, to test every corner cases, to fix some issues. So it took 2.5 years to implement this optimization. And now the interesting part is Python 3.6. I didn't try to sort optimization by the gain. I just wrote a list of the optimization. So the first one is a change that I made on the memory allocator. So to understand that, you have to know that we have two kinds of memory allocation functions. There is the PyObject family and the PyMem family. And the PyObject used an allocator called the pmalloc, which is a fast memory allocator for objects smaller than 1 kilobyte, and objects which has a short lifetime. It's really efficient. If you try to disable it, it makes Python something like 20% slower. So my idea was simply to use the PyObject allocator on the PyMem family. But it was not that easy because the PyObject requires to hold the GIL, the global interpreter lock, and the PyMem was using the system malloc, which doesn't require any kind of lock. So to be able to change that, I was asked to test some third-party applications like NumPy, Django, LXML, Pillow. And the good news is that I only found one bug in NumPy, and it was quickly fixed. And to make sure that we don't make any issues, I also implemented a new test. So in the debug mode, you are able to check if the GIL is held by your application. So it makes sure that you use correctly the API. So on many benchmark, the code is between 5 and 22% faster, which is quite good only by changing 2 lines in the code. And a very cool side effect of the change is also that you are able to get the debug hooks in the release of Python. Because when you develop a C extension, sometimes you get buffer overflow, but you may not be able to detect them as a first run because memory overflow are like random. So using the environment variable pydebug equal debug, you are able now to enable the debug hooks and to detect different kinds of issues related to memory allocations. The next optimization, in fact, is a follow-up of the PyCon Canada 2015, made by Break Cannon. The keynote compared Jython, EuroPython, PyPy, CPython 2, and CPython 3. And Brett noticed that one specific benchmark was much slower in Python 3. So he reported the issue. And Sergei Storchaka, as usual, was very fast to identify the bug and to produce an optimization. And the optimization simply made the code twice faster, which is quite good. Another more complex issue is profile-guided optimization. To understand that, the idea is that you compile Python twice. First, you compile Python using specific compiler options to say that we will trace the execution of your code. And you run a specific task with this custom Python, and you compile Python a second time using traces collected by the execution. And the idea is that using traces, you give hints to the compiler to say that maybe this code is it's called often, it's a hot code. This code is never called, so it's cold code. But also, even at a single conditional test in the code, the tool is able to say that if you have two blocks, the true block and the false block, it is able to say that one block is more likely. And if one block is more likely, the compiler is able to exchange the two blocks or to tell to the CPU that maybe you should optimize one case in favor of the other. And what Brett made on the PGO compilation is that instead of using the p-digit program, which basically computes digits of the p constants, he changed that to use the Python test suite. And the thing is that the PyDigit only tests a very few functions in Python, which are related to compute integers. But if you use the Python test suite, you cover a lot more. You have a much better code coverage, and so you are able to know much better which code is hot or not. And the effect of this change, in my opinion, is very important because it's between 5 and 27% faster only by the compiler. So it means that you don't have to modify your Python code, you don't have to modify your C code. It's just that if you use the compiler correctly, it makes the compiler emits machine code much more efficient. So it means that we have to be very careful on the compiler on how to use the CPU correctly, because maybe we can still do better. The next optimization is called word code. In fact, Sergei Storchaka proposed on the Python IDs mailing list to change how we store the bytecode, because in Python 2.5, what we had is that depending if an operation has an argument or no arguments, it took between 2 or 3 bytes. And the thing is that in the very hot code of Python, the loop which evaluates the bytecode in the ceval.c file, before executing each instruction, you have to check if you have an argument or not. And if you have an argument, you have to fetch the next 2 bytes. And this is not something good for performance because you introduced conditional code. And the CPU has to guess if we will take the branch or not. So what was decided is simply to always use 2 bytes. So Dimur, Humed, and Sergei Storchaka changed the bytecode to always use 2 bytes. And simply, if you don't have an argument, just put 0 in the arguments. And so we were able to remove this conditional code in the very hot part of the C eval. Fast call has a different story. In fact, we had some crashes in the code on specific optimization of Python. Because in Python, the thing is that to call any C function, you have to create a tuple. And I expected the tuple to be very quick, very cheap, because we have a free list to avoid memory allocation. We have a fast path to optimize whatever we can in the creation of a tuple. But in practice, creating and destroying the tuple takes 20 nanoseconds. But if the function is really fast, something like 100 nanoseconds, 20 nanoseconds is significant. So we had an optimization trying to cache the tuple, to reuse the same tuple for all calls. But using a cached tuple created a lot of corner cases which were very tricky to work around. So what I try to do is to just remove the tuple and pass directly a C array of pointers. So you don't have to change reference counts. You don't have to allocate memory on the heap. You can allocate memory on the stack, which is much faster. And obviously you don't use tuple, so you don't have to call the garbage collector. And I was surprised that it's really faster. And on many micro benchmark, it's between 12 and 50% faster. To give you some example of optimized function, is like getting the first item of a list. It's like getting an attribute using the getAttr function, the get method of a dictionary, the count method of a list, the replace method of a string. So in fact, a wide range of functions were optimized just by avoiding the tuple. And the other cool thing about that is that you don't have to modify your C code, because many functions were optimized internally. So you just have to use the C API, and it's getting faster. For Unicode codecs, the story is that Naoki Inada reported an issue because he is working on a PyMySQL. And in PyMySQL, he's decoding data from the database. And to decode data from the database, he wanted to use the surrogate escape error handler. But if you do that, you are getting bad performance. So I looked at the code, and in fact, I found very inefficient code, and I was able to optimize them quite a lot. For example, for the UTF-8 codec, the decoder is 15 times faster, and the coder is 95 times faster, which is quite good. And the ASCII encoder, the ASCII codec, the decoder is 60 times faster, and the coder is 3 times faster. And in a Python 3.5, we decided to reintroduce bytes formatting. Basically, it was for the Mercurial and the Twisted projects who use bytes in many places to discuss on the network or on the file system. But the code was inefficient, so I developed a new API called the PyBytes Writer. Basically, the idea is to be more smart in the way you allocate memory, or maybe even avoid allocating memory to work only on the stack memory. And using this API, the formatting becomes twice faster, and for example, the fromX method to create a bytes object became 3 times faster. Globbing is the operation of listing the content of a directory using a pattern like give me all JPEG pictures. And to optimize that, Sergej Storchaka used the new os.scandir functions. The idea of this function is that it not only returns the file name, but also the file's attributes. So on Unix, on Windows, you don't get the same attributes, but the idea is that at least you are able to know if the file is a regular file or a directory without any further syscall. So the glob function is between 3 and 6 times faster, and the passlib glob became between 1.5 and 4 times faster. For async IO, Yuri Selivanov and Naoki Inada identify that we create a lot of future on task functions, and we create them, we destroy them. So the idea was simply to re-implement these functions, these classes in the C language. And just by doing that, the async programs are now 30% faster, which is very good. And to finish, the optimization made in Python 3.7. The first one, it was made by Yuri Selivanov and Naoki Inada. It's to add a new opcode to load a method and to call a method. The idea is that internally we can avoid some operation and make the code more efficient. So the method calls became between 10 and 20% faster. But the idea comes from PyPy, who implemented this idea a few years ago. We had a lot of ideas to optimize Python even further, but I prefer to not discuss them here because I'm not sure that we will implement them. I'm not sure that they are really efficient, so just stay tuned. And now the bad slide. I have a bad news. We still have some benchmarks which are slower, but I will not go in depth in this benchmark because in my opinion, they are not really bottleneck for your application, but you have to know that we are good, but there are some cases which are maybe 10% or 20% slower. And the interesting part is a very high bar. In fact, it's a Python startup. On Python 3, we are something between 2 and 3 times slower for the Python startup. Even if we made very, very good progress on that part, we are still slower, so we have to find a way to optimize that. If you want to know more about that, you can go to the speed.python.org. You can browse all data, you can compare Python version, you have access to the timeline. And there is also a website which are basically my notes, how to optimize Python. And I also explain why we cannot implement some optimization. Do you have any question?
Everyone, please thank Victor. So we have time for 1 to 2 questions. So if you think you have a really good question, please line up at one of these microphones in the aisles here. Yeah, over this side.
Hi, thanks for the talk. Am I on? Yeah, cool. I was wondering if you can speak to what the outcome of the FatPython project was and kind of what we may have learned from it.
The question is about PyPy?
Oh, no, the FatPython project.
The FatPython project.
Yeah.
In fact, I started to work on benchmark because of FatPython. To explain you, I was working on a project which is a compiler ahead of time, which generates a specialized code using guards check at runtime. And the idea is to emit better bytecode by using some assumption on the code. But the thing is that I was not really able to check if it's faster or not. So I preferred to focus on benchmarking and maybe also focus on a much simpler optimization. But I'm still working on that as a side project.
And that is all the time we have for Victor. So please thank him again for a wonderful talk. And we'll be starting up here again in about 10 minutes' time.
OpenStack, one of my job is to port OpenStack to Python 3. And the good news is that most unit tests pass already on Python 3. So we have close to port this giant project, which is something like 3 million lines of Python code ported to Python 3. And sometimes I'm also working on Python. So we will first start to discuss how to get stable benchmark. We'll receive the results of the different Python version to finish with the optimization of the different version of Python. So benchmarks. 1 year ago, in March 2016, In fact, almost no one trusted the benchmark of Python because if you run the same benchmark twice, once it will take that the benchmark makes Python faster, and the second time it will say that the benchmark makes Python slower. So we didn't know if we should trust them, and some people just decided to only focus on micro benchmark or just hope that maybe it will make Python faster. So to fix this issue, I started to write a new module called perf. The perf does different things. First is calibrate the number of loops to run the benchmark long enough. It spawns multiple processes in sequence. It computes 3 values per process, so to get a total of 60 values. It's important to spawn multiple processes because, in my experience, each process will get different performance, and it's nice to have all kinds of values to be able to get more stable results. Which
we begin, just another reminder, please check your phones, laptops, anything that makes annoying noises during talks. Make sure they won't make annoying noises during talks. And actually look at your phones, take them out of your pocket. Make sure they're quiet. That'd be really useful. Thank you. We'll just wait for these last few people to come in, and then I suspect the doors will close. So welcome to the first of these stream sessions at PyCon 2017. Our first presenter today is Victor Stinner, who is going to be telling us about optimizations which made Python 3.6 faster than Python 3.5. Please make Victor welcome.
So hi everybody, I'm here to tell you which optimization made Python 3.6 faster than Python 3.5. I'm Victor Stinner. I'm working for Red Hat on an issue on your benchmark, or maybe that you have an issue on your system. The performance project is a new project hosted on GitHub. It's a new version of the benchmark suite, now using perf. And the good news is that the speed.python.org is already running performance. So to get stable results, my first issue was the code locality. It's something related to very low-level stuff of the CPU, because depending on the exact layout of the code in memory, you don't get exactly the same speed. And to get stable results, you can use LTO, which is a link time optimization, but also the PGO, profile guided optimization. And the other kind of issue means more reproducible results. What you can do with all these values, in the old version of the benchmark suite, we use the minimum. But if you use the minimum, there is a known issue called the local minimum, which is that if you run the benchmark once on the benchmark a new time, you don't get the same value because you need a very long list of values to really find the minimum of your computer. And if you use the average, it's much more reliable because you smooth the values between the maximum and the minimum. And another important tool coming from statistics is the standard deviation. It gives you an idea of the range of where most of your values are. And it also gives you an idea of the stability of your benchmark. Because if the range is too big, it probably means that you have